Okay, so now I will show you how to use the graphical interface, which is named Daiquiri. In the future, you could log to Daiquiri directly from your laptop, independently of the ESRF Wi-Fi, but it's not yet fully implemented. So for the time being, you can log as long as you are at the SRF. And if you would be at home, or in the lab, or at the hotel, you can log, but with a remote access. Okay, so the web page or the web address is this one. Okay, so I will log. When you log, you see your experiment, and for the Beamline staff, an additional one. So we will go to the user experiment. And here, the main information is the image given by the optical microscope. So basically, we have just mounted a sample, and we would like to find regions of interest over this sample. We can possibly start with a very large mosaic, such that we see all the, let's say the samples mounted together. So before doing that, I will just change a bit the illumination such that we are not fully saturated. So you have two lights, the light in transmission here and the light which is in reflection here, but this one is usually hidden by the X-ray fluorescence detector. Another way to reduce illumination is to reduce the exposure time. So you can change this value, and then you have to click enter. If you have not clicked on enter, the modification is not taken into account. Okay, so now I have an illumination which is acceptable, and I would like to use the mosaic to acquire a set of pictures to let's say, cover the mosaic. So I would like to use this mosaic, but I would like to draw a rectangle larger than the field of view. If I use the roller of the mouse, in this case, I can zoom in, but I cannot zoom out for the reason that the video here is clamped. So if I declamp it, then I can zoom out. And then I see a workspace which is larger than just a single field of view. As soon as I'm going to acquire something being a mosaic, being X-ray maps or XANES, the results, the images or the scans will be associated with a sample name. So it's very important to give a proper name to your sample or samples to be sure of where the data is saved. So we can call it, for example, like Mount 1, because here we have many samples together. Okay, add sample. Then I will draw a rectangle. So mosaic has been selected. I will draw a rectangle, maybe something like this. Then I say start. For example, if we realize that there is a part which is missing here, we can draw a second mosaic, and then it will superimpose everything together. So at this zoom, because now we are at the minimum zoom times 1, it's relatively slow because the y-axis that we call SAM-Y, which is here, is relatively slow. It's faster in vertical. So I can use this time to explain you a bit what you can see in this interface. So you see 6 important motors starting with SAM. SAM means sample. You see SAM X here, SAM Y, SAM Z. So these ones, they are stepper motors, they are in millimeters, and these are the ones which are going to allow us to move a lot over the sample stage. So typically SAM Y and SAM Z, they have ranges of about 15 millimeters, but they are not super accurate. They have an accuracy in the range of the micron. So if you want to have high resolution maps, you should better use the piezo motors. And these are the motors which are named SAM PY, SAM PZ, the P for piezo. And these ones, they are in microns, as indicated here and there. They are much more accurate and reliable than the stepper motors, but their range is limited to 100 microns. So the system will automatically select the appropriate motors if you draw a map. If the map is less than 100 microns, and more particularly 99 microns, it will use stepper motors. If it is less than 100 microns, it will use piezo motors. The fifth box is zoom for changing the zoom. So we have basically ×1, 6, or 12. When you start and when you have no idea about your samples, you can start with 1, but as soon as you want to have something precise, you should go to 12 and then be sure that the focus is well down, because the beam is not orthogonal to the sample. It's under an angle of 60 degrees. And so if you are not well focused, you will have some parallax effects and you will be shifted horizontally. So when you are working on, let's say, details and you want the best resolution maps, the focus, optical focus is very important. So if you would like to change the zoom, you select it and then you click on move. I will not do it now because the mosaic acquisition is ongoing. This is to change the exposure time, and it should always be in acquiring mode. If, for example, you have the impression that the image is static and it's not refreshing, it's maybe because somebody would have clicked by mistake on live. So always keep visible light microscope acquiring. Backlight, so here you have the possibility to change the intensity of the light in transmission, and here's the possibility to change the intensity of the light in reflection. Don't worry if the light is still on when you launch an acquisition. Daiquiri starts any acquisition with recording an image, so turning the light on, taking an image, turning the light off, and then starting X-rays acquisition. So you should not worry about the fact that the light is still on when you start an acquisition. Here we have the possibility to go to few specific positions, but probably you are not going to use that. There is no reason. It's more for the staff to prepare the beamline. It's not for you. Okay, so the mosaic is almost finished. So now we see more or less the different samples. So in the meantime, we can zoom in and we can also move in the workspace, not the motors, but at least the image like this. So we can zoom in and zoom out like that. Okay, so here, if we think that we are missing a part of the samples, we can add a small mosaic here, for example, like that. And then we have the complete view. So then we will have to decide with which sample we want to start, where we want to go. So you can also take the time spent on the acquisition of the mosaic to define all the sample names. So the sample names are given under this small symbol here. You just have to click on add sample and provide a name. So if you can give me the names of all the samples which are in this month 1. So then we have to decide with the one with which we start. Okay, so we will start now with some acquisition on the sample SS18. So first we need to locate it. So if I go to this sample, I just see the image of where we are now. I don't see the full mosaic. To see the mosaic, you need to come back to month 1. So here you see all the entire mosaic. So if I select move, then we can click directly to the sample of interest. So we can already start to zoom in to better see things. So even if it is moving, let's say not laterally on the sample stage, in the meantime, we can change the zoom. Okay, so maybe I should have gone, maybe I will start with a region which is just at the edge, such that we have a good contrast for changing the focus. Okay, now we see something, but it's very small. So an easy way to get the image full size is to click on video fill. And you have two options. Either it's filled in, let's say, x-axis, or if I click again, it's filled in y-axis. Okay, so here we see together the superimposition of the optical image of where we are now superimposed with the mosaic. So maybe now I can go to sample SS18. And from now we have only the display of the optical image. So it's not well focused. Here you can, you have the SAMX motor. The X direction is perpendicular to the sample surface. So it's a way to make the focus, to be sure that if the sample is well focused optically, it will also be well focused with respect to X-rays. Okay, so here we are not too bad in terms of focus, but I want to be sure that it's perfect. So I will move to the maximum zoom. Here you can choose the step with which we are going to do iterations to adjust the focus. So here I have 100 microns, and I will see if, yeah, it's getting better, I think. In a normal situation, it should be around 0, but for the specific case of your experiment, we are close to 2 millimeters. So now that we know that the surface is well focused, because your sample is very big, I can move back to zoom 6 such that we have a large overview of your sample. But if your sample was small, we will say with a zoom of 12. Okay, now we could also repeat, and this is maybe what we can do now, a mosaic at this magnification. So something maybe like this. And then we have to find a region of interest. Okay. But then we may need to use the light in reflection. So now we would like to acquire a map. To do so, we will use this rectangle region of interest. However, this will impose a size. And then when we are going to acquire a map, the software imposes that you have an integer number of steps. So if we anticipate that we would like steps, for example, to be 5 microns, it's good that you select already here 5 microns. Okay. Then you are sure that the map size is a multiple of this number. It's not critical in the sense that you can always change it manually, but it saves time if you anticipate more or less the size of the pixel. So for example, here I will select a pixel, let's say a pixel of 5 microns, and we can maybe draw a map, something like this, maybe. Okay, so you see that now I have a new selection with a number, and this number is given here, and any acquisition, being a map, being a XANES, will be associated with a specific number. So, and this number is unique. You can repeat the map 3 times, and the name of the file will be this one, and then another number, just to see first with which region of interest or point of interest the acquisition is associated with, or but also to be sure that you have a unique object. Okay, so here we have the name or the number of the map, which type it is, and the size. We can still change the size here. So for example, I could say I want a square of 700 in both directions. If you change the values, don't forget to click on the green button, otherwise your modification is not saved. And you also have the possibility to change manually the SAM-X value. As the one which is given here is the one which was there when you drew the rectangle. Okay, so we could define as many regions of interest as we want, covering different regions, something like this. If you know that you want to select a series of maps and you don't want to click systematically on region of interest, you can force the system here to keep a record of this action, and then you can draw as many regions as you want. If you want to delete a rectangle, you can just click on it, as long as no data is associated or has been acquired on this region of interest. If a map has been acquired, you cannot delete the region of interest anymore because it's archived somehow. Once you have the rectangle, the region of interest, you click on New, and here you have a couple of parameters to choose. The dwell time, typically for concentrated samples, we can go down to 20 milliseconds. For not very concentrated sample, we could go up to 100 milliseconds, to 200 milliseconds. So let's start maybe with 0.1, just to start. Here you will give the step size in horizontal and in vertical. It is not necessarily the same. If you would have, I don't know, a high heterogeneity in one direction and not in the other direction, we could adjust it. In your case, to start, we are going to say 5 and 5. By default, the fast axis, the one where the motion will be continuous, is horizontal. There are very few cases where we want to force it to vertical, but it's only if the motor range is below 100 microns, which is not the case here. Here you select the detectors that you want to use. So in your case, it's very important to have FX2, which is for the fluorescence detector, and P201, which is for the photodiodes, which are measuring the beam intensity. The other ones are not so important. Here we will have the possibility to add some attenuators. So this is something we can test to be sure that the dead time is the same from one sample to another. Before running the map, it's better to check that. If we want, we can say, okay, the attenuator we need for this specific map is aluminum 6 micron, which is the one which is now. If you would have a different flux condition for two samples that you would put in a queue, you could say, okay, this sample high flux, this sample low flux, by forcing the system to change the attenuator. Another way to change the beam intensity to modulate the dead time is to modify the size of the horizontal and vertical slits. So that would be another way we could do that. And the last thing which can be of interest, maybe in the future, if we want to run maps at a specific energy, and for example, map sulfides and map sulfates, is that we have the possibility to select a specific energy, set a specific energy for maps. Or we can also program it in a very, very, let's say, structured way, such that you have tens of energies if you really want to have the 2D spectral or speciation information. Okay, once you have defined the conditions, you can either start the map immediately, execute now, or you can queue it. If you queue it, you will see that here you have one action which is queued, and then you can run it. You can program as many maps as you want. If you have 10 samples mounted together, you can program all of them together with different names, at different focus, with different step size, with different acquisition time, with different flux conditions, at different energies. So when a map is running, you can display a couple of things. So first I will declump, voilà, such that we don't have the image always moving. And then I can move in, and then I can, voilà, something like that. Okay, so let's see the results of this map. You have two ways to display results. Those counters which have been predefined in the main system, which are here under this flag. So all these counters. Or you can use the Daiquiri region of interest tool here. And here you can say, okay, I would be interested in, for example, the silicon K alpha and sulfur K alpha. For example, you can always add more elements. Another way to do that can be to use a history. And if you have already selected region of interest for another element, you can call them back. Okay, so once you have your region of interest, click on close and you will reload or regenerate maps. And now we see already some results. List here. You always see the last one with this purple eye selected. So here the map we see is sulfur. If I click on this one, the one we see is the one above, which is silicon. Okay, I could possibly add, I don't know, aluminum if it is relevant. Close, close, and then refresh, and then the last one is aluminum. You have the possibility to create red, green, blue, so superimposed display. If this is relevant, if you are looking for some co-localization of some elements, to do that, you click on the 3 maps that you would like to superimpose. And then you have this tool here, where you can choose which color will be associated with which element, and if you want to play on the opacity level. If you do that, then you have a new image here, and which is the one which is shown here, that you can also hide or display as you want. The update is not automatic because it was making some crashes. So if you want to update manually, I mean, you can activate it, but you have a risk of crashes. So I would recommend not to activate it. But if you want to refresh it, you just click on regenerate, and then you have image again. So all these maps, they are associated with this region of interest and with a particular number of acquisitions. So you see here, this number here, 2007, 27,547 is the number of the scan which is here. So now if we look at PyMCA, if I go to the sample SS18, so first you see that we have one folder for the mosaic and one folder for the map which is running, and one H5, which is this kind of H5 files which are just making links to the real data. So again, this one is very light here, but the real data is much heavier, as you can see here. Okay, so I move up. Tack. Okay, so we see that now we have a scan, which is corresponding to a map. We see it by two ways. The name contains Roy for region of interest, and the description is L2 scan. L2 scans mean it's a 2D map, 2D scan. It shows that how the map was acquired, some Y starting ending position number of points, and then some Z starting to ending position number of points, and then the time per pixel. We cannot open it now because it's still ongoing, so it's not blue yet, but then we could. I can already show you which kind of counters we will find, which are basically the same as the one we had for the XANES. So I can possibly add this counter and this counter, which will be relevant for the rest of the experiment. Then I can add as well, if we want, silicon. Okay. Okay, so now the map is finished. And indeed, we could, so we see that we have particles with sulfur, and we see also the silicon glass matrix. One question can be, okay, was the dead time good? And the attenuators were selected. So if I go back to PyMCA, okay, let's have a look at the map. We are in this sample, this file. Again, I will redefine the user counter. So we want to have some Y, some Z, possibly the dead time, and we can take sulfur. So here I say it's a 2D image, Y, Z, and then this one, replace. So that's the map of sulfur. We could see here, replace the map of silicon. Just that with respect to Daiquiri, it is upside down because by default, PyMCA display the motor positions with increasing values to the top. Now the question is, was the dead time good and the attenuators well chosen? So if I want to show that, replace, here we will check the value. So in the glass matrix, in the blue region, we have values between 20 and 30%. So that's absolutely perfect. If we would be interested in the particles, clearly the dead time is too high, and we would need thicker attenuators if we want to acquire XANES on these particles. But let's consider that for now, we are interested only in the glass matrix. So if I come back to Daiquiri, then I will use the point of interest tool, and I will click about 40 times in the glass matrix, such that we have a good statistic of spectra. Okay, so now we have 40 points. If of interest to you, we can add points on the particles if you want, but then I have to change the attenuator conditions. So then I will move. So I select move, I go to a specific particle. Okay, and here I will use the Bliss interface to count and to see the dead time. So I call back the last command. And here I have a dead time, which is 54%. However, yes, this is at a sulfate energy. So this one will be too high typically. So then it means that I would need to change the attenuator. So we have a command for controlling the attenuator, SXM attenuators, multiple position. If I just type this name, I see that now we are on the aluminum 6 micron attenuator. Let's try to see if an attenuator of aluminum 12 microns would be good. So I select the one with 12 microns. It takes a few seconds to go to this attenuator, and then I recall the previous command with a count. And then we will see if the dead time is acceptable. So here, indeed, it's attenuated and maybe too much. So alternatively, what we can do, I will go back to the 6 microns. 6 microns. We have another set of attenuators, which are not in the main hutch, which are in the CC5 hutch. So the name is CC5 attenuators. Now I have no attenuator. Maybe I can try to add 3 microns aluminum. This way I have 6 plus 3, 9, which may be a good balance between 6 and 12. So if I go to CC5, yeah, we can accumulate them. Aluminum 3 microns, back. Okay, and then let's see if we have a better net time now. That time 22%, so we could work like this. So we can consider that for the concentrated samples, the best would be to test it. I mean, maybe the flux condition will be a bit different here on a very hot spot. So if you would be really interested in all these particles, you may spend more time thinking, okay, maybe 12 microns, 9 microns or whatever. But at least for a first observation, we can run like this. So we say for the glass, 6 microns, and for the particles, 6 plus 3, let's say. A last detail is the fact that the beam intensity is measured with this counter here, I0. This one, the photodiode is downstream CC5, upstream CC5 attenuators, upstream SXM attenuators. So whatever SXM attenuator, it will not impact the I0 intensity. However, the 3 microns attenuator of CC5 have decreased the intensity of I0. And usually, I mean, we like to optimize the gain of the photodiode such that this intensity is between 1 million and 10 millions. So here, clearly, it could clearly be higher. So to change the gain, and if you want to test it, you type K for Kesley. And then if you want to know what the gain is, you can interrogate it like this. It's 7. In this precise case, I guess I could go to 9. Okay, so if I count again, now we are at 3 millions, which is perfect. So in the case of an attenuation 6 plus 3 microns, we should put the gains of iodate at, in this case, at 9. Now, if I remove the 3 microns attenuator, I will check the gain again, and maybe it will be a different one. We will see. So here, the problem is that in these conditions, I have basically 10 millions. It means that the photodiode is saturating. In the case of the glass, where we have only 6 microns attenuator, we could use a gain of 8 in principle. Now you see that it's no longer flashing. And then, so if I count again, we have 1 million, which is good. So it means that basically we will be in 2 flux and gain conditions. 6 micron attenuator and gain 8 for the glass, for the points on the glass, and 6 plus 3 microns attenuator and again 9 for the points on the particles. So here I have already selected points in the glass, so we can take note of that. So the first one is, so if you select all the points like this, they will turn yellow in this interface, which may be easier to read. And so if you click on images canvas, it will send this image, this picture to the logbook. If I go back to the logbook and I refresh it, you see here the image, which was on Daiquiri interface. Okay, so we are ready to launch video field. Okay, so now we have to make sure that the conditions are not the same for the points in the glass and the points on the particles. So I will select all the points which are not in the particles. So I think it was up to this one. So I will be sure that all the points in the glass are yellow and the other ones, they are blue. And then you click on new. And either you define manually the conditions, or maybe it was previously defined if you have a former acquisition in the same conditions. But in this case, there is no history, so I will do it manually. Here we work at the sulfur KH. So the starting energy will be 2.46 kV. And so this plus something in it, so 0. And we would like to go up to 253. So I will say plus 78 EVs, step size 0.2, and dwell time 0.1. The counters which are important to record in your case are FX2, which is the X-ray fluorescence signal, P201, which are all the counters, the photodiodes, which are in particular measuring the beam intensity. Calc FX2 is very important. GOT Bragg 2NA is a counter which is going to give the energy position. And the last one can be interesting if we want to be sure that the monochromator was working in the best conditions. These counters, anyway, they are saved. So as soon as this acquisition is launched, this is in the history, so you just have to reload with this button here, and all this will reappear again. Here you have the possibility to change the number of repeats, but in the present case, we are going to use only one repeat. It's always better if this option is taken. So if there is whatever problem, it will not stop the full queue, it will proceed. And here, that's very important. This is where we are going to say that for the points in the glass, we want an attenuator of 6 microns and a gain of the I0 of 8. And then I will say Q. And then we will select the last, I don't know, 10 points. We will keep the same condition for the XANES, except the attenuators and the gain. So, okay. Now, if I go down, oops. I go down. So what you see is that now all these points, its returns have been queued. So there is an acquisition which is queued, not acquired yet, but in the list. So if I take the last points, we check that they are all on particles. The queued one now, they are yellow, and the new ones, they are orange. New, refresh. I have all the previous conditions, and here I have to say 9. And I should say that on top of the SXM attenuators, we have a CC5 attenuator, which is aluminum 3 microns. Q. And now we have a list of something like, 51 points in this list. What could you do? You would have the possibility, for example, if for whatever reason you would like this point to be the first, you can click here. You can search that goes to the top of the list. You can move them by one step up or down. You can add a pause. You can delete a specific point if you want. So you have the full possibility before launching the queue, and also while the queue is running to modify it. This is to completely clear the queue. And when the acquisition is running, and we can start it. So it starts. So when you see this running, it means that acquisitions are ongoing. So it always starts with a picture of the sample, then it turns off the light, and then it will start the acquisition. So here, if you would click on this one, you will kill only the XANES which is ongoing, not the entire queue. If you want to stop the entire queue, it's this one here with the beam. If we want to follow during the acquisition the results, then we go to another panel, which is here, Scan Viewer. Under Scan Viewer, you have the list of all the acquisitions which have just been done. So the CT which are here were the ones that we did for the checking the dead time. And here you see the first XANES. So to get the good display, you need to select as x-axis GOAT BRAC2 NA GOAT, as y-axis the calculated FX2 counter. So it's the sulfur X-reflorescence corrected by the dead time and corrected by the beam intensity. And you have to make sure that either you are at 1000 or all points. So here you can see the first spectrum being acquired. Progressively, you will see that the number of elements in the queue will decrease as long as the acquisitions are ongoing. Finally, here you have all the history. So it's a good way to check if an acquisition has been done and if it was successful. So in the best case, all these pages will be green. If there are technical issues, you will see it easily that it will be orange, like failed, or red, I don't remember, over pages. But for the time being, all the things that we have done were successful. Okay, so if you want a higher resolution map from this low resolution map, just reselect region of interest. Maybe one is enough. Draw a rectangle around the region of interest, and then go in your list. Here, okay, here this map is more than 100 microns. So if I would start it like this, it will be scanned with the stepper motors, which is not good because the stepper motors are not super accurate. So it's easy to change it to 100 microns, and indeed I would advise to go to 99 because this way we are sure that it will be acquired with piezo motors. Okay, it's up to us to decide the step size. So new, then I will reload, and then here I guess I can go faster because we saw that the sulfur was concentrated, and I can possibly say, okay, a pixel of 1 micron in both directions. Since the beam, when it is well focused, is in the range of 0.6 microns, we could easily reduce the pixel size further. But for the demonstration, we will keep 1 micron. I will keep this. That's, I mean, you should fit the pixel size to the beam size. Right. Okay, so since we are interested in very concentrated hotspots, in particular here around the sulfur sulfate particles, I will add this second attenuator, and then I will set the gain to 9 for I0. And well, it should be pretty fast. So execute now. And so we will have a second map superimposed with the first map. And since we already have regions of interest which have been defined for the first map, for this map here, I can simply just refresh. And in principle, the list of region of interest is already integrated in the graphical interface. So here you already see directly silicon and sulfur. So again, if I clamp and if I zoom in, then we should see
the high quality.
Alors, this is sulfur. So I can refresh. And this is silicon. So you will have exactly the same, but at higher resolution. And because the range is small, and because we are using piezo motors, the acquisition is pretty fast. So it will take a few minutes. And then if you would like something heterogeneous, like surface effects, if you would expect, I don't know, the speciation to be different in the center of the particles and in the surface of the particles, this is something we could study. We could select points of interest specifically in the core of the particles or around them, if you would be interested in some surface effects. We could also, if you expect, for example, the interface to have a different chemistry with respect to the core of the particles, we could acquire XANES on different points at different locations, but also a map at several energies, maybe at minimum 2 energies, such that if you have a contrast with speciation A and B, and if you have the species A, which is over-absorbing for one energy and B for another energy, we could acquire the same map at 2 energies and then superimpose them and get a qualitative idea of the respective distribution of the 2 species. So for sulfur, it works very well in the sense that you can easily see sulfides and sulfates, for example, because the difference in energy is very high between these 2 species. Okay, so by refreshing, you can, let's see the results, and here we clearly see the details of the particles superimposed with a low resolution image. And at the end, it is automatically refreshed, so that even if you are not here during the acquisition, when you arrive, let's say in the morning, you should have all the maps, because Daiquiri itself refreshes the display at the end of each one.